scooped out here by Glaciers. Let's see if we get some pictures of Mount Edith Cavell. There we go. So those rocks came from somewhere, were part of this mountain once. And they would have been from up near the top, because the assumption is that at the time they were quarried, most of these valleys were completely filled with ice. So it'd be interesting, and I haven't done this, but I would guess you could go maybe using OSL, looking at just the geomorphology and actually finding the spot where these, if you were to reverse, if you were to play this film backwards 15,000 years and then see this stuff going back up and then becoming part of the mountain, where exactly was it? I don't know. But you can actually see, and I have looked on Google Earth. We maybe should pull that up in a minute. Let's see if I close this out. Maybe, is it going to focus for us? Well, there's plenty of candidate locations of where this sculpting could have taken place. But you have to transport it through this valley here, and look at the floor of the valley. You see these long linear trends? And look up here, you can see, oh, yeah, here very clearly the results of this catastrophic flow through this valley. You can see it very clearly right through here. So you had water flows coming down. Let's see, there's Mount Robson right here. Oh, yeah, now we're getting it. Now we're starting to get some resolution. So it could have been anywhere along this, probably along this southwestern flank. That if Robson was the source, this southwestern flank looks like it would have been the most likely location. Like, look at this right here. This could have been quarried out right here. Google Earth could probably tell you something. But in any case, either way, you can see that the rivers converge right here and then flows up to the north. And oh, you look, you see the flat floor here, that's all sediment left. Comes out this way, and we should be able to actually find the channels, probably, let's see, through here, because I don't know exactly where the Laurentide front was, but it was somewhere out in here. And that's why the water couldn't keep flowing east. It had to get turned to the south. And then Okotoks got dumped here. So there would have been a very large iceberg necessary to transport Okotoks. So the size of that iceberg might give one a idea of the magnitude of this flow that's coming through here, because that iceberg is probably the size of a tanker ship that's carrying this as its cargo. Now you got a picture that the final stages of that process is that the iceberg is being swept along in the flow, and because it's the biggest iceberg, it probably was one of the first ones to come to ground. But so the iceberg comes to ground literally, right? It stalls at some point because as the floodwaters are declining, it's losing its competency to transport mass. So the first thing that settles out is going to be the heaviest and biggest stuff. So the iceberg comes to ground. It's in a bed of soft material. But then the iceberg itself has to melt away. Now, it might take years for that iceberg to melt away. But bear in mind that that iceberg melting away is also going to keep the substrate, the ground underneath, perpetually wet and soft until the iceberg is gone, and then the modern climate regime can come in and all of that. But so the final stage of this process is actually rather slow and gentle, because the force to create this flood and the armada of undoubtedly hundreds or probably thousands of icebergs being carried along, the water flow had to be enormous. There had to be a lot of icebergs because every iceberg isn't going to be carrying a rock. So you probably got, for every rock, you probably got 10 or 20 or more icebergs being carried along in there. But there's enough rocks to show that there had to have been more than just melting of the glaciers, because you have to impose enough force that you're going to fracture the flanks of the mountains, the shoulders of the mountains protruding above the ice sheet. So how do you do that? I don't know, other than I could speculate, and I would speculate some type of an impact event, whether an atmospheric explosion or actual impacts. But where would you look for actual impacts? I don't know, other than if we go north of here, you'll notice you've got this long trough, and you can see that the valleys are all interconnected here. See this? Look at this. Okay, but then you trace this channel north all the way up to here, and you get up to Prince George. And all of this area up in here, let's see, where's Prince George? Let's zoom out. There it is, Prince George, right there. And there's something interesting going on when you start looking at the landscape around Prince George. And here you can see what we're getting into. Do you see what we're looking at here?
Yeah. Chevrons.
Drumlins.
Drumlin.
Thousands and thousands of drumlins. We've looked at drumlins, haven't we?
I think we've actually looked at Prince George very briefly before.
Now, drumlins are a paleocurrent indicator. They can tell us which way the water is flowing. The blunt end faces of a drumlin, the blunt end faces up current, faces upstream. So if you're looking at this, what was the direction of flow that sculpted these drumlins?
The blunt end faces upstream.
Yes, the blunt end faces the direction that the current is coming from.
Yeah. Well, they're coming south.
Do you see a blunt end? When I say blunt end, look at this right here. This is blunt. You see this? This is the blunt end, and then you have a tapered end. Look at these. These are more clear. See, the south ends of them are blunt, and then they taper as you go north. So this is telling you which direction. Now, these are subglacial flows we're talking about. This is a movement, massive subglacial water movement has created this landscape that you're looking at here. And which way is this flow going? It's going south-southwest to north-northeast. And it's coming right up here, headed like it's going straight for Prince George. And you see that over here, the top end of the Rocky Mountain Trench, and it goes all the way down, all the way down, all the way down, all the way down to Flathead Lake. And then it opens into the basin here. The Mission Basin, it's called, because these are the Mission Mountains here. And at the south end of Flathead Lake, you've got this hummocky stuff, which is terminal moraine. And I think we've defined terminal moraine, haven't we?
I believe so. I know we've defined moraine.
Right. There's more rain, and then there's less rain. And if you have no rain at all, it's known as a drought.
Right.
Okay. Good. I'm glad you're straight on that.
Thank you. Thank you.
So
what is terminal moraine? Just to be clear.
So, we'll look it up. Terminal moraine. So, first of all, let's define moraine. Moraine is the ground mass that's created by the glacier grinding over and pulverizing the landscape. The terminus of the glaciers, where the snout of the glacier, where the glacier ends, right? That's also called the zone of ablation. It's where the tip, the end of the glacial tongue tends to melt back as fast as it's growing, right? The moraine that piles up at the glacial terminus is called terminal moraine. So right here you have terminal moraine. And what this terminal moraine that you see right here does is it tells you that this was the southernmost extension of this lobe of ice, because here's the moraine right here, and you can go through it. I've been through this many times, and we take groups to outcrops to show. There's some great outcrops where you can just really say, okay, this is moraine. Doesn't seem very interesting because it's just there's nothing there except a jumbled mass of incoherent stuff, chaotic stuff from sand to gravel to cobbles to boulders to other kinds of stuff, but mostly that. And there's no structure to it. There's no architecture. There seems to be no stratification to it. And that is how you distinguish a deposition from a glacier, because it's a structureless mass from the deposition of water that will usually have some kind of architecture within it, showing bedding and sorting of the constituents of the deposit, right? So structure, architecture in water flow, chaos, no structure in glacier flow. So moraine, but see, here's where drumlins get interesting, because drumlins start out as incoherent, chaotic, jumbled, pulverized glacier mass, subglacial mass. But then you look at a drumlin field and there's structure to it. Like, just compare what we just saw with drumlin swarms compared to this. Well, there's some structure here, right? You can kind of almost see that there's kind of a recessional effect going on right here. So you've got this mass here, and then probably a short passage of time, because this glacier is now melting back, right? After the catastrophic disruption, which completely causes the conversion of large amounts of glacier into, first of all, water, and then, of course, solid chunks of ice. But then after a period of time, the point I guess I'm trying to make here is that we could estimate maybe a quarter, maybe a third of the I don't think as much as a half of the glaciers are destroyed in these convulsive events. Because what happens is, it seems like the convulsive event separates two glacier regimes. One is that prior to that, the glaciers are living glaciers. You have a zone of accumulation, you have a zone of ablation. In the highlands, the glaciers are accumulating. Each year's mass of snow adds to the growth of the glacier. The weight of that pushes on the glacier and causes a dynamic flow downhill all the way down to the snout of the glacier, where most of the melting takes place. In between the zone of accumulation and the zone of ablation, there's this inflection point, the equilibrium point, where the transition occurs from the glacier growing to the glacier shrinking. Right, that's called the equilibrium line. So in colder times, the equilibrium line goes up. In warmer times, the equilibrium line comes down. Okay, so if it comes down, it's going to be more readily melting. But in either case, you see what you've got right here is terminal moraine. We can zoom out, and we can go, let's go up here. We can see here's another example of terminal moraine. So what happened was you had this major glacier lobe coming down, and it trifurcated into three sublobes. One of them got diverted right back to the northwest. One of them got diverted to the west, and another one got diverted to the south. The one that diverted to the south left its calling card in the form of this moraine, called the Polson moraine. This lobe terminated right here. You can see Look, here you've got the flat outwash plain that was in front of the glacier snout, and here's where the glacier snout was.
Mm-hmm.
So all of this right here is lateral moraine because it was on the side of the glacier. Then this is the terminal moraine right here. And there was a natural breach of meltwater through that terminal moraine, which provided the most convenient and economically feasible place to place State Route 28. So here's an example of, humans coming by thousands of years later and taking advantage of the features in the landscape that were created by these natural events. But interestingly, there was another major flow. We looked at this, came down right through this way, and just like the glacier lobe was here. So when this water flow came down and hit the glacier lobe, it was diverted to the west, and you can trace its path right down this way. And it flowed out. So if you were looking at this over at the time this flood happened, this would have been a Nunatak right here, right? All of this was buried under ice, and now you've got this major subglacial flow coming from the north here.
So why did it divert to the northwest? Why did one of the lobes divert to the northwest?
Well, I would imagine that, if you look at this is a smaller lobe than this lobe, and that's a smaller lobe than this lobe.
I see.
Right, and it was probably just because if you can see here, the mountains are bottlenecking, so that means that the ice would have been piling up here. Right, it's being fed from the ice is continuing to flow south. The big main trunk has got this big glacier flowing south, right? Well, when this diverts to the west, what's happening, it's trying to go into this V-shaped valley. You can see how the valley is getting narrower. Mm-hmm. So that causes the ice to pile up. And when it does, the path of least resistance probably was this to the north. However, when that lobe did divert to the northwest, it left its own hand, sculpting of the landscape. And I mean, you can see where the glaciers ground their way around this way. And then you can come up here, and here's terminal moraine right up here. Right? And then you had this huge flow that came down, and prior to that flow, this ridge would have been all connected. So this island wouldn't have been an island. It would have been a continuous ridge going right up here. This right here now is a 500-foot cliff. This trough, you can see this was a spillway right here. And right here where there's a lake that occupies the bottom of this trough, this spillway trough, because as the water rounded this curve, it was particularly turbulent. And because it was turbulent, it was able to erode up the bottom of the channel quicker, you see. So you've got a scour trough right here, and there's another one right up here. So this was a water flow, a pathway. So you can chart all this, and this is where Google Maps and Google Earth and all comes in so handy. Because, a few generations ago, we didn't have these tools. So all of this is just this clogging of sediment that occurred between the mountain ridge here and the thick glacier lobe here. So you had this trough between them. So that became a conduit, and it flowed down, and the whole floor of this valley here has all of the sculpting of the sides show the turbulent vorticular motion of the water as it's moving through. It was choked with sediment because when the floodwaters finally subsided, it left this flat area here. And if you were to dig down, if you were to flush all of this out, you would have seen that pre-flood it was a V-shaped valley floor. And if you filled this up, 200 to 300 feet, there's probably 200 to 300 feet at least of a flat sedimentary floor in this is called Big Draw here.
Okay.
And on our Montana tours, we follow this route because we follow the route of the floodwater.
And so then it filled up with 200-300 feet of sediment, making it flat.
Yes.
Yeah.
Yep. And then, look, the water gets diverted to the south right here and flows down through the Little Bitteroot Valley.
And it's diverted because is there a glacier there, or is there some type
Yes,
of
there's
harder
probably
rock?
the glaciers would have been probably right in here. I don't know exactly where they were because part of the problem is, and I haven't been up here. This could be remnants of moraine here. I haven't been up here. I've been down 28 many times, but I've never gotten out and explored intimately this area up here. But it's likely that, if you picture this is buried in glaciers here, that glacier line is going to come across right in here. So, yeah, you're going to have these mountain glaciers that are part of the Cordilleran ice sheet. This is probably where they stopped right here, right? It would make sense because right here, the glacier lobe is usually going to project further south than just the normal edge of the ice. You'll have the normal edge of the ice sheet, and then in places where the topography is conducive, you will have these tongues flowing off, right? And so those create those glacier lobes. So it's most likely what you're going to have is the glaciers are covering these mountains, but there would have been enough open area in the valley here that this water came down, rushing down, and then it hit these hills right here. And you can see that there are several places where the water breached the hills. Right here, and here you see some scour trough lakes right here, Schmidt's Lake. Where else? There would have been a flow that came down this way as well. And if I go to satellite view and I zoom in, we looked at this. Remember this?
Yes.
There's your giant current ripples.
Mm-hmm.
And you can actually see there's multiple mega flows coming through here. So look at this. Here's a mega flow coming through here, right? Here is a mega flow. You can see it. Look, two flows right here. Here's one. Here's one. They're almost conjoined right here at the hip, and then they separate down here. The peak here of the depth of this water through this Camas Prairie here was we can know because we know the elevation above sea level of the basin floor, and we can trace the high water mark up on the valley walls, and on the mountain walls the high water mark was at 4,200 feet above sea level, 4,200.
Wow.
So the valley floor is 2,800 feet above sea level. So from that, we can determine that it was the water at its maximum depth coming through here was 1,400 feet, 1,400 feet deep. And it's 5 miles wide there, and it's probably moving at 40 to 50 miles an hour. And it would have been choked, again, with icebergs. But see this, so now we've kind of raised an interesting question. I've kind of showed you this connection now between the Rocky Mountain Trench, at its south end, is feeding into Lake Missoula,
Yeah.
and at its north end is up here on this interesting terrain up here that's characterized by these massive drumlin swarms. Now, could all of this be related to what's going on over here with the foothill erratic trains? I would say it's almost 100% certain.
It would
Now-
be quite the coincidence if not.
If not, yes. But you see, here's the thing. Here's again, mainstream. Does it just like in the same way? Bonneville flood and Missoula flood are two separate, unrelated events.
Yep. Oh,
Well-
here's another one.
Here's another. This event, if we want to call it the Calgary flood or the Athabasca flood, I call it the Athabasca flood because of the Athabasca River.
Right.
Well, is that also unrelated? But if it's related to the Missoula flood, and the Bonneville is in some way related to the Missoula flood, then they're all three related to each other, aren't they?
I would think so.